All right, so we are on topic 1.6, photoelectron spectroscopy, and it's just a method for figuring out the energy that an electron has within an atom or molecule. And the way that this is done is kind of using the law of conservation of energy, because if we hit a sample with a known amount of energy, so some high energy photons hit this sample, they knock an electron free. Let's just say hypothetically the energy of this photon is, 3 millijoules. It's probably much less than that, but that 3 millijoules hits the sample, it knocks the electron free, and that electron now has 2 millijoules of kinetic energy. Well, if 3 millijoules came in and then the electron had 2 going out in terms of its kinetic energy, then what happened to that 1 millijoule of energy unaccounted for? Well, that must have been the energy holding the electron to its positive nucleus, also known as its binding energy. So the binding energy of the electron is equal to the energy of the photon coming in minus the kinetic energy of the electron after that interaction. And if you remember, the energy of the electron comes from, E equals h times nu, Planck's constant times frequency. But, it's just the energy of the photon is really what that's saying. You don't really have to use this equation. We're just kind of using it to explain the concept. All right, so let's talk about photoelectron spectroscopy and electron configurations. So let's say we have lithium, which of course we know is just 3 electrons, so 1s2, 2s1. The Aufbau principle says that we're going to fill the electrons into the lower energy level sublevels first, or lowest energy sublevels first. So using the diagonal rule here, we would put 2 electrons into the 1s, and then we put electrons into the 2s, and if we had more, we would keep going to the 2p and the 3s and so forth. So that's the Aufbau principle. The lowest energies sublevels gets filled. Lowest energy sublevels get filled first. All right, now let's look at a little PES graph here. So a couple things we need to know about this graph. Let's look at the y-axis and at the x-axis and see what we learned here. So we have relative number of electrons. So all we really know if we're analyzing this graph is that this peak, whatever that represents, is twice as big as this peak, and then it means relative number of electrons. So whatever this represents contains twice as many electrons as this. But if we think about what we know about electron configurations, we know that the maximum number that we can put into the first sublevel, into the 1s, is 2 electrons. So this peak represents the 1s, and it contains 2 electrons. So if the y-axis is relative number of electrons, and we already know that the first little peak here should represent the 1s2 holding 2 electrons, then even if we didn't know this was lithium, we should be able to figure out that this would represent 2s1 because the peak is half as tall as the 1s2. In other words, it holds only 1 electron. So even without the y-axis being labeled, we know that this represents 2 electrons and 1 electron, right? So the position of the peaks gives the energy needed to remove an electron from a sublevel. So if we look at the x-axis here, we have, first of all, the numbers running kind of in reverse of what we're used to. The 0 is over here on the right, and we have a much larger number, in this case 100 over here on the left. Just think of the nucleus as being over here on the far left. The closer you are to the nucleus, the harder it is to remove an electron. So these 1s2 electrons are going to take a lot more energy to remove. You can see maybe 7 or 8 megajoules per mole of electrons that you tried to remove. If we compare that to a much smaller number in the 2s to remove that electron. And then the height, again, the y-axis is proportional to the number of electrons in that sublevel. So here we have 2 and here we have 1. So that would mean that our electrons are at 1s2 and 2s1. Okay, so having looked at one PES graph, let's take a look at another one. See if you can figure out using a periodic table what the electron configuration and the identity of this atom would be. Okay, so hopefully you looked at this and realized that my first electrons would be way over here on the left. The numbers are much greater this time, and that is because we have a larger atom with a larger nucleus, and that means that its 1s electrons would be held in with a lot more binding energy, because Coulomb's law tells us that the larger the charge of that nucleus, the more tightly that electron is held in place. So this apparently has a lot more electrons and therefore a lot more protons, and so each electron is held in place more tightly at a given sublevel. So this would be 1s2, right? And then big gap here, and then we would come to 2s2, and then this very tall peak is 3 times bigger. That's because this would be 2p6, and then another pretty large gap, and then we would have 2 more electrons in the 3s2. All right, so if you said 1s2, 2s2, 2p6, 3s2, which would correspond to magnesium, that would have been correct. Okay, let's take a look at 2 different elements, beryllium and magnesium. They are right above and below each other on the periodic table. Beryllium, as we can see here, has 4 electrons. Magnesium has 12. So let's take a look at what we can kind of learn from comparing these two. So first of all, beryllium is just 1s2, 2s2. That's its whole electron configuration. All right. Its 2s2 electrons are at 0.90 binding energy. So if we look at where that peak is, that's already been estimated for us to be about 0.90. Okay. And then if we look at magnesium, first of all, its electron configuration we could figure out by saying, it's all right, 1s2, 2s2, 2p6, 3s2. This is the one we just looked at. But its binding energy, and even if you didn't have that number written above there for you, you could probably compare it to the valence electrons in this beryllium over here and realize that, yeah, the beryllium's valence electrons, or the beryllium's, last couple of electrons here are almost at a binding energy of 1 versus substantially below 1, right, for magnesium. So why are magnesium's valence electrons not held as tightly? And it gets back to Coulomb's law. So Coulomb's law says that force of attraction is going to be proportional to the 2 charges over the radius squared. So in the case of the 2 charges, we're talking about one being an electron and the other being the positive nucleus. And so if we look at why magnesium's valence electrons have a smaller binding energy, well, we've got a couple of reasons. Well, one main reason for that, and that is that it's in the 3rd energy level. So the further away you are from the nucleus, the weaker that binding energy is going to be. So here we see the radius is causing, as radius increases, force decreases. So if we're in the 3rd energy level, like we are with magnesium's valence electrons, that force is going to be much smaller than if we're only in the 2nd energy level like we are with beryllium. Now, that also, though, brings back to, okay, well, what about charge, though? Because the charge of a nucleus, the charge of a beryllium nucleus is only positive 4. So if we consider an electron to be negative 1 and the nucleus to be positive 4 for beryllium, versus the the magnesium, which has a positive 12 nucleus that electron is attracted to. Well, why doesn't that make the magnesium? Why doesn't that make the magnesium's valence electrons held more tightly in place? And the reason is because of the much larger radius of the third energy level compared to the second. So radius, you can see it squared, is going to have a bigger impact than the difference in charge between a magnesium nucleus and a beryllium nucleus. Okay, let's take a look at an example problem. So this is a complete photoelectron spectrum of an unknown element drawn X above the peak that corresponds to the orbital with electrons that are on average closest to the nucleus. Justify your answer in terms of Coulomb's law. So go ahead and pause and do that, please. Okay, so hopefully you would draw your X right above this first peak. Now, you might be tempted to justify that answer because you would say, oh, well, that's the 1s2. That's the closest to the nucleus. Well, that's true, but they're asking you to justify it in terms of Coulomb's law. And so by justifying it in terms of Coulomb's law, you would simply say that those would have to be the closest electrons to the nucleus because their binding energy, their force of attraction to the nucleus is the greatest of all the electrons on this PES graph. So as radius goes down, force goes up. All right, and then write the complete electron configuration for this element. Go ahead and give that a shot. Okay, so you should have said something like 1s2, 2s2, and then this would of course be 2p6. You can see it's about 3 times taller. Then we have 3s2. Now be careful here. This is a little tiny one here. It's only got, it looks like 1 electron. So this is going to be 3p1. And this one didn't ask us to find the electron or to find the element, but that would be aluminum, right? 3p1. Okay, and then finally on the graph, draw the peak. So it's asking you to actually draw in your own peak corresponding to the valence electrons of the element that has 1 fewer proton in its nucleus than the unknown element has. So think about that. Draw your own peak for the valence electrons that are just 1 element below aluminum. Okay, so we know that we're not going to have that 3p1 peak anymore because we're taking away 1 electron. And this is no longer aluminum. This would be magnesium. Now, there's one other change other than the 3p1 being gone. I hope that you thought about this. Maybe you didn't, but the peak should be drawn in a little bit lower, smaller binding energy position than what we see for aluminum. And hopefully it makes sense why. Because magnesium only has 12 protons, and so the binding energy for those 3s2 electrons would be a little bit smaller than the 3s2 electrons in aluminum. So your valence electrons in magnesium would be a little bit lower binding energy, and you don't have to know the exact number. They just want to know that you understand that with one less proton, the binding energy goes down just a little bit. And so you would draw it just to the right of the 3s2 peak that you had for aluminum. And that is topic 1.6.